Why economists love the Cobb-Douglas function? Ever wonder why some production functions are more popular than others? Let's talk about Cobb-Douglas function. Its flexible returns to scale and famous constant elasticity of substitution. What's the most versatile tool in an economist toolbox? For modeling how inputs like capital and labor turn into outputs, it's often the Cobb-Douglas production function. But what makes it so special? In this video, we're going to explore two of its superpower, its flexible returns to scale and its famous constant elasticity of substitution. Let's break it down. The first key property is its return to scale. What happens if we double all our inputs? Let's scale both K and L by a factor T. We plug Tk and Tl into the function. After factoring, we see the output is scaled by t to the power a plus b. This is incredibly flexible. If a plus b is equal to 1, then t to the power 1 means constant return to scale, double inputs, double outputs. If 1 is less than a plus b, it's increasing return to scale, doubling inputs more than doubles output. If 1 plus 1 is less than greater than a plus b, is decreasing return to scale. This flexibility allows economists to model all sorts of real-world industries. The second great feature is the Cobb-Douglas is linear in logarithms. By taking the natural log of both sides, we get the simple linear equation. This isn't just a matrix, it's a huge practical advantages. The coefficient a and b now have a direct economic meaning. They are the output elasticities. A is the elasticity of output with respect to capital. A 1% increase in capital leads to an % increase in output. Similarly, B is the elasticity for labor. This makes estimating the function with real data much simpler. Now, for the main event, the elasticity of substitution, sigma, this measures how elasticity a firm can swap capital for labor while keeping output constant. Think of the curvature of the isoquant. If they are perfect complements like laptops and programmers, it's hard to substitute. Sigma is close to 0. If they are perfect substitute like pencils and pens, it's easy. Sigma is very high. So there does Cobb-Douglas fall. Let's prove it exactly in the middle. With sigma always equal to 1, the proof starts with the marginal rate of technical substitution, MRTS. The slope of the isoquant is the ratio of the marginal production. Let's calculate the marginal production of labor, which is the partial derivative of Q with respect to L. Next, the marginal product of capital. Now, the MRTS is MPL divided by marginal product of capital. Watch as term cancel beautifully. The A cancel out the K term simply to just K in the numerator. The L term simply to 1 by L. And we're left with the elegant simply formula MRTS equals B by A times the capital labor ratio K by L. The simple relationship is the key to find the elasticity. We work with logs, taking the natural log of both sides, giving us linear equation. Now let's rearrange it to solve for ln K by L. The elasticity of substitution sigma is formally defined as the percentage change in the capital labor ratio divided by the percentage change in MRTS. In calculus term, it's the derivative of ln K by L with respect to ln MRTS. Look at our equation. Ln K by L is a linear function of ln MRTS with a slope of 1. The derivative of a variable with respect to it is always 1. Therefore, sigma equal 1. It's the straightforward. So, let's step back and appreciate what we have learned. The Cobb-Douglas function isn't just a random equation, it's a carefully crafted tool that hits a scientific sweet spot. It's utilized in the combination of three fundamental properties. First, as we saw, its return to scale are perfectly captured by the sum a plus b. This isn't just a mathematical curiosity, it's what allows economists to model diverse real-world scenarios. We can model a small artisan workshop that might have decreasing return to a competitive firm in constant returns, or a tea grain with massive increasing returns to scale, all by tweaking just two parameters. This flexibility is its first superpower. And this is crucial. Its elasticity of substitution is constant and equal to 1. Think about what that means. It describes a world where capital and labor are neither perfect complements like two pieces of puzzles, or perfect substitutions like two identical brands of petrol in street. They are imperfect substitution. A 1% change in the relative price of labor to capital leads to a 1% in the capital labor ratio. This Goldilocks level of substitutability turns out to be a remarkable useful starting point for modeling actual economies. It's a simplifying consumption that is strong enough to be useful but not so rigid that it's on learning concepts for you. It would be huge help if you could like this video. It tells YouTube that this content is valuable and you are studying economics. Consider subscribing to the channel. I am here to break down complex topics into clear step-by-step explanation. Thank you so much for watching. Leave a comment below if you have any questions and suggestions for what we should explore next. Until the next video.